Hi there, I am Alex Burke.
I'm Caleb Nahori.
Hi, I'm Scott Murphy.
Hello, my name is Dahlia James.
A common problem is that there is not enough time to prepare a meal. Preparing a meal is often extremely time-consuming and challenging process. The meal preparation process often involves repetitive and predictable tasks based on recipes. Our meal preparation robots will solve this problem. In this slide, we have the design requirements for our meal prepping robots. The design shall be able to fill a glass of water in less than 20 seconds. The design shall be able to butter the bread in less than 20 seconds. The design shall be able to toast bread. The design shall be able to notify the user when the meal is ready. The design shall be able to clear and set the table. The design shall be able to clear the table before and after meals. In this slide, we go over who is responsible for which robot. The ToastBot is created by Scott Murphy. The Prepping the Meal robot is created by Dahlia James. The Drink Dispensing robot is created by Caleb Nahori. The Buttery robot is created by Alex Burke.
ToastBot by Scott Murphy. This is ToastBot, the robot that I've designed, and the goal of ToastBot is to pick up a piece of bread, toast it, and then deliver it to the plate of the person who's having their meal prepared. If you take a look at that first picture, you will see a couple of the important features called out. ToastBot has 4 wheels. It also has a center section that is the red portion in that picture, and that is the toaster part of it. So you look at those blue wedges, and those are the doors. They open downward so that the ToastBot actually has the ability to scoop up bread and then deposit it by lowering a door and then moving away. And it will scoop up the piece of bread, leave it in the toaster while it finds the plate that it is to be deposited on, and then it will deposit the bread there. Also, it has a distance sensor on either side, those small lighter blue rectangles on either side, and those are used to detect how far ToastBot is from the bread or the plate that it is depositing the bread onto. This is the circuit that controls ToastBot. First thing you'll see in the top left there is 2 ultrasonic distance sensors. As we said before, one of those will be on the front and one of those will be on the back of the robot, and they will allow it to determine how far it is from the piece of toast it is picking up and the plate that it will be depositing the toast onto. Additionally, if you look in the top right, you will see 2 servo motors, and those are used to control either door on either side of the robot. You'll also see there's a 9-volt battery involved, which helps us to power the actual motor to make sure we get enough power. And then in the bottom right, you will see the actual motor that allows the robot to move forward and backward. ToastBot's behavior will follow this flow chart. So we'll start off, and then we will go to check if there's toast inside. This is the primary function of ToastBot, so it needs to know at all times if there's toast inside. If there is not toast inside, which will be the default setting, it will then check, is the front distance, the distance between the robot and the bread, greater than 10 inches? If it is, the robot will move forward and go back to the start. If the distance is not greater than 10 inches, the robot will check if it is between 10 and 5 inches. If it's between 10 and 5, then the robot will lower the front door, move forward to pick up the bread, and then raise the front door to seal that bread inside the robot. And then it will go ahead and go back to the start of the program. If the front distance is not between 10 and 5 inches, meaning it's less than 5 inches, the robot will move forward to make sure that it scoops up the bread, and it will raise the front door, closing the bread inside, and then it will go ahead and restart. Going back to, is there toast inside? If there is toast inside of the robot will check the rear distance, the distance between itself and the plate, and if that distance is greater than 5 inches, it will move backward or towards the plate, and then we'll go back to the start of the program. If the rear distance is not greater than 5 inches, the robot will be close to the plate, so it will lower the back door, leaving the bread there, or the toast there rather, and then it will move forward away from the plate to allow the bread to stay, and then it will raise the door up once it is away from the toast and the plate. The next step is that it will transmit a signal to the Buttery robot, letting it know that the toast has been deposited, so that way the Buttery robot can go ahead and move forward with its section of the program. And then the program will restart from there and can make more toast as needed. This is the actual code that will be sent to the Arduino powering ToastBot. So it will control the actual robot. We already went through the functionality when we went over the flowchart, but here it is to get a better and fuller understanding so you can glance through that real quick. So this is going to be an actual demonstration of the code in action. First, you will notice that because we are more than 10 inches away from our piece of bread, the motor is turning in that direction. And as we approach the piece of bread, when we get within 10 inches, you'll see the door opens and the motor stops. And then after a second, the motor sort of starts moving in little tiny motions, getting closer and closer to the bread with the door down so that it's able to scoop it up. Once we get within that 5-inch mark, showing that the door has fully gotten underneath the bread, you will see the door here close, and the engine actually starts to move in the negative direction. From there, the robot is moving towards the plate instead of the bread. As we approach the plate, once we get within the 5-inch mark, you will see that our second door opens, allowing for the bread to be deposited, and then closes, and the engine starts moving away from the bread as the bread has been deposited on the plate. You'll also see in our status monitor that the toast has been deposited, and that message is sent out to the buttery robot.
Hello, my name is Dahlia James, and I'm here to present Prepping the Meal Robot. The robotic arm is a device that can be used for various applications. I built this robotic arm using the Arduino Uno board and a micro servo, and I will be showing you how it works. Component. To build the robotic arm, I used several features, including the Arduino Uno board, the micro servo, the LM7805 voltage regulator, and various capacitor and resistors. The Arduino Uno board is a microcontroller board that can be programmed to control various electronic devices. The micro servo is a small motor that can rotate and move different parts of the robotic arm. The LM7805 voltage regulator regulates the voltage from the battery to a stable 5V power supply for the servo and the Arduino board. The capacitor and the resistors are used to filter out the noise and ensure that the circuit functions properly. Circuit. The circuit that I use to power and control the robotic arm is relatively simple and effective. Circuit. The circuit that I use to power and control the robotic arm is relatively simple but effective. I connected the 5V pin on the Arduino Uno board to the plus rail on the breadboard and the ground pin to the minus rail on the breadboard. I connected a digital pulse wide modulation pin on the Arduino Uno board to a row on the breadboard and inserted the 10K resistor between the digital pulse modulation pin and the ground rail on the breadboard. I inserted the micro servo into the breadboard and connected the positive pin to the rail on the negative pin to the negative rail on the breadboard. I connected the signal pin to the micro servo to the same row on the breadboard as a 10K resistor. To power the circuit, I connected the positive terminal of the 9-volt battery to the terminal 1 input pin of the LM7805 voltage regulator and connected to the negative terminal of the 9-volt battery to the ground rail on the breadboard. I inserted the 10 UF electrolyte capacitor between terminal 1 input pin of the ML7805 voltage regulator and ground and the 0.33 UF ceramic capacitor between terminal 2 output pin of the LM7805 voltage regulator and ground. Challenges and solution. While building the robotic arm, I encountered several challenges, such as issues with wiring, coding, and understanding how the component work. To overcome this issue, I did some research and consulted with my teammates. I also experienced with different solutions until I found one that worked best for my project. In conclusion, building this robotic arm has been rewarding, an experience that has taught me a lot about electronic and programming. I am excited to see where this project can go in the future and how it can be used to solve real-world problems. Thank you for your time. And here is the flow chart. Here is the code I used to program my robot.
The Drink Dispensing Robot by Caleb Nahori. In this slide, we have the design for the drink dispensing robot. On the left, we have the main robot where it has the tank to hold the liquid, the photoresistor to let it know if the glass is full, and it also consists of the motors to dispense the liquid and to move it back and forth on the track. On the top right, we have the lid that goes on top of the robot. And then on the bottom right, we have the track that the robot goes onto, where it has the force sensor to let it know if the glass is on the sensor, and it also has 2 photoresistors to let it know where it is on the track, and it also contains the Arduino. For the circuit, I have 4 photoresistors, 1 force sensor, and 3 DC motors, all connected to an Arduino board. The flowchart for my robot shows that it doesn't start moving till there is a cup on the sensor. When there is a cup on the sensor, it will go across the track to where the cup is and start filling it. When the cup is full, it will go back to the opposite side of the track where it started. This is the code for my robot. It will also be continued on the next slide. Right now I have 4 sensors showing that there is a cup on the sensor, and right now this one is saying that the glass is not full. And this one is saying that the robot is not over there. So it will turn on that motor, which will bring it over, and when it gets all the way over, it will cover that sensor, which will turn off that motor. And then it will start filling the glass, which is that motor at the other end. And when it's full, either by the force sensor going up, saying that is that the weight for a full glass, or this one sensor showing that the glass is full, which will turn off that motor. And then this one will bring it back to its starting position, which will turn on the reverse motor. Then when that sensor is covered, it will turn off that motor.
This is the battery robot. There's a lot of components that go into the battery robot. Therefore, I'm going to break it down component by component and then explain how they all work together. On the first picture, you see the front of the blade, the body, the axles that are connected to the wheels, and the ultrasonic sensor. On the second photo, you see the blade, the ultrasonic sensor, the Arduino board. The Arduino board will connect the motor, the micro servo, as well as the wheels and the ultrasonic sensor. On the third picture, you see the blade and the wheels from the side connected to the frame, and you see a part of the Arduino board. The way that this robot works is that once a piece of toast is approximately a few inches away, the motor will continue on going until it is about 0.2 inches away. At that point, the micro servo will activate to send the blade from side to side 4 times, that way to get all of the butter applied to the toast. Once this butter is applied, what will happen is the robot will back away a good enough amount of distance to get that blade out of the way, turn, and then move forward to get out of the way of the toast. Therefore, the most important components inside of my design are going to be that blade, the micro servo, the ultrasonic sensor, and the motor, and how those work together. In addition to this, the ultrasonic sensor will act as a stop and go system in case anything gets close to the blade as the robot is traveling away. If a person puts their hand in front of it or something gets in the way of the robot, it will stop. This activates as partly a safety feature as well. The goal of this robot is to be small, compact, and allow for maximum output as it is buttering the toast, therefore providing an optimal experience to the user. These are the circuit boards to the battery robot. The ultrasonic sensor, as it senses something getting closer, will stop at about 0.2 inches away and activate the micro servo on top of it. The bottom picture explains the motor details. One motor will be connected to an axle, which will allow it to move forward. When the ultrasonic sensor detects something in front of it, it will automatically be programmed to stop the robot. The robot is powered by a 9-volt battery, which allows the robot to continue moving with ease and with no issues, and then once the battery is low, it can be easily exchanged. This will make the robot super easy to maintain and be long lasting. And here is the flowchart for my robot.
When it comes to collective behavior, our robots generally function independently, although they are working towards a communal task. I separated each of the different robots into their own color in this flowchart. You'll see that the purple is ToastBot, the yellow is the buttery robot, blue is the drink dispensing robot, and then green is prepping the meal robot. So the only two that truly interact with one another are ToastBot and the buttery robot, and that is because ToastBot transmits a signal to the buttery robot after the bread is deposited on the plate, so that way the buttery robot can go in and butter that toast. The drink dispensing robot and prepping the meal robot mostly function on their own because they do not actually need communication from the other robots to do their specific portion of the work.
The entrepreneurial aspects of this project are extremely important to go over. Total cost of the project with all of the prototypes being built is $369.69. This is calculated using Amazon to look up all of the parts, including all sensors, boards, wheels, and everything, and just to get the project off of the ground. The parts build cost chart up on top will show how much of each component went into it. We see that the Arduino board was the most expensive part of the project with most of the cost, which was upwards of $140. Down on the bottom, you're going to see a pie chart, which will show all of the robots and how each price went in each of them. As you can see here, the butter robot was the most expensive, and the least expensive was the meal toaster, which gets us to that magical number of $369.69, which gets our project from start to finish, all built up, done, and ready for the market. Add in probably about $10 to $15 for packaging, and you are set. The meal prep robots are not an existing project, which is actually what provides value to the customer. This provides value to the customer because the average consumer is spending about 10 to 15 minutes per day prepping breakfast. This cuts that down by that 10 to 15 minutes, allowing the consumer to spend 10 to 15 more minutes sleeping in, getting ready, and doing what they need to. This also lowers the stress of consumers and allows them to enjoy their life a lot more. When it comes to convenience, consumers are willing to spend a lot of money on these robots. Look at robo vacuums, robo lawnmowers, and other different robotic programs. This is the next step to providing value to our consumers' lives.
Summary. The meal prep robot collection is designed to address the time-consuming and challenging meal preparation process. The collection consists of 4 robots: ToastBot, prepping the meal robot, drinks dispensing robot, buttery robot. The robot work together to complete the meal preparation process, including toasting the bread, preparing the meal, filling drinks, applying butter, and clearing the table. The robot communicate with each other to ensure that each task is completed promptly and efficiently. The final design and algorithm will result in a seamless meal preparation experience for the users, providing them with much time to do other things. User-centered design. We started by conducting user research, which involved interviewing users and analyzing competitor robots to understand users' needs and identifying opportunities for improvement. Ideation. Based on the research findings, we brainstormed different design concepts and created rough wireframes and sketches to explore other design solutions. Prototyping. We then created a low-fidelity prototype using a prototyping tool to test our design concept and gather user feedback. Design. We used the feedback from the prototype and testing to refine our design and create a high-fidelity mock-up of robot design. This included incorporating visual elements such as colors, typographic, and imagery to create a visual appealing design. Testing. Finally, we tested usability to ensure the design was intuitive and easy to use. We used the feedback to make any necessary revision to the plan. And here is the reference.